Hello everyone, my name is Sergio López-Ureña and I'm a researcher at University of Valencia, Spain. Today I'm excited to share with you my work on growing neural networks without forgetting, using a subdivision-inspired solution. Let's dive in. Neural networks are mathematical functions with lots of adjustable parameters. By solving an optimization problem, they can learn very complex patterns from large volumes of data. You may have heard how successful they are in tasks like image recognition or natural language processing. As we tackle harder problems, our networks grow larger. This means more layers, more neurons, more parameters. But bigger networks are harder to optimize. Your training takes longer and finding the right structure becomes a strategic research challenge. How many layers should we use? How many neurons per layer? Which activation functions work best? One idea is progressive training, where we iteratively grow or shrink the network as we learn. Suppose you already have a well-trained network. You would like to add neurons or layers, but you don't want to throw away everything it has learned. That's called a function-preserving transformation. We create a new, a deeper or wider network that gives exactly the same output as the original for every input. Before continuing, I would like to give a warning. I'm a mathematician and I'm just getting into the field of neural networks, so it's possible I have and I will use some terms incorrectly. I'm sorry. And you will see that the content of this video is very mathematical. Do not expect to find an educational video from now on, but rather a talk at a scientific conference. Also, this video is like an experiment I'm conducting to try to give more visibility to my research. So, as you may have noticed, it is very amateur as well as my English. I'm very sorry. Let me recall some basics. A layer operator L takes an input vector x in R and 0, multiplies by a weight matrix W and adds a bias B and applies an activation sigma component-wise. So L of x equals to sigma of Wx plus B. Common sigma examples are the identity function, the ReLU, or the sigmoid. A multilayer perceptron, or MLP for short, is just several of these layer operators composed one after another. Our goal, given the multilayer perceptron P, build a new network bar P that's deeper or wider, but satisfies that equals to the original P for every input x. In this presentation, we will focus on how to add neurons in an existing layer. For further details on this work and even to know how to add new layers between existing ones, I refer to the original paper that I left in the description and you can find at the end of the video. Consider two consecutive layer operators L0 and L1 so that they are connecting three consecutive layers of neurons. We want to insert extra neurons in the middle layer. The mathematical description of this enlargement of the layer consists in defining two new layer operators, L0 bar, L1 bar, so that the domain that is in between both is larger. It consists of N1 bar neurons instead of N1. What we want is that the composition of these new layer operators exactly coincides with the composition of the previous layer operators. In this way, we obtain exactly the same outputs from the same inputs. To introduce in this matter, let me show you how we could do this very easily, despite this is not very convenient in practice. We start by writing the L1 operator. By definition, this is sigma 1 applied to Wx plus B1. And we conveniently write this matrix multiplication Wx by columns. So denoting by W semicolon comma 1, this is the first column, W semicolon comma 2 is the second column. This matrix multiplication can be expressed as the sum of these columns multiplied by x1, x2, xn. In this way, we can easily see what is the contribution of each neuron, and, well, we can imagine how to easily insert a new neuron. So just imagine that there is s plus 0 times xn plus 1. In this way, the output of L1 is still the same, clearly. Okay, so L1 bar is defined exactly as L1, but just adding a 0 column to the weight matrix. Now, how can we define L01? Let's write what we have. This is the formula for L1 bar we already defined. Let's compare how is the composition of the new layer operators that we have to define and compare it with the composition of the original layers. Comparing both lines, we see that L0 bar must be equal to L0 for all components I from 1 to n1, but the component n plus 1, since it is multiplied by a 0, because this is the definition we take for L1 bar, then it doesn't matter the value of L bar 0. So we can define it freely, for example, as 0 again. This was just an easy example about how new neurons can be added. Many authors have addressed this problem, for instance, zero padding, that is like the one we saw, just put many zeros, but they realize that there is some initial performance drop in the training process. Other authors, for instance, consider tensor decomposition, but this is a computationally expensive solution. Let's see what is our proposal. Our proposal consists in considering a new class of activation functions that enable the creation of layers and neurons, and it is based on subdivision theory. What will be the advantages? That we will obtain an explicit and efficient formula for the parameters computations, so an easy formula to compute the W matrix and the bias coefficients, but also, since the subdivision theory is grounded on approximation theory, we expect that the resulting multilayer perceptrons have good approximation properties, and the creation of new neurons gives an advantage in this sense. Okay, the key concept here to add new neurons is the refinable property. We say that sigma is a refinable function if it fulfills this formula that says that the function can be expressed as a linear combination of the function itself, but scaled with a factor of 2 and shifted with tau L. So the key idea is that sigma can be expressed with a copies of itself, each one scaled and shifted. And we will see that this allows to split each neuron into new A neurons. To see that this property can be achieved easily, we start by proposing two activation functions that fulfill the refinability property. One is this one, the spline activation function of degree 1. We define this as spline activation functions as, well, this formula, and clearly see as in the graphic. It is piecewise linear. In 0 it's equal to 0, and beyond the value 0.5 it is thresholded. And we see in the second formula that it certainly fulfills this refinability property, which graphically can be shown as here, where the red line plus the green line will return exactly the blue line. Another example is the spline activation function of degree 2. In the paper that we refer, it is in the description, it is also defined the spline activation function of degree n. Again, what we see is that it is piecewisely defined using polynomials, in this case second degree polynomials, and again it fulfills the second line refinability property, where the blue line is the sum of the red, green and orange lines. To give an additional example, just to highlight that the classical identity function that is very used as activation functions fulfills the refinability property, and in fact it fulfills in many ways, that is, with many possible linear combinations. Okay, what is the idea behind this definition? Well, suppose that you have this function that can be defined as a linear combination of the spline activation function of degree 1. You see that it is just a polygonal, and in some way a multilayer perceptron is the composition of several of these polygonals. Well, something oftenly done in approximation theory in order to increase the approximation capability is to add new nodes. Nodes are here represented by the red dots. So that if you insert, for instance, a new node in between the old red nodes, you have more nodes, and you could further optimize to find the best place for the new nodes so that the function is better approximated. And this addition of nodes can be expressed mathematically in the formula by using the refinability property. You are just splitting its activation, its function sigma, in several sigmas but scaled, so that you are localizing the effect of each one. So, how can we use this refinability property in order to add neurons? That, remember, it consists in defining new layer operators so that the composition of them is equal to the composition of the original layer operators. Well, according to this theorem that is in the paper, you only need one thing. That is that the first activation function, sigma 0, is refinable. In that case, you must define L0 and L1 using these formulas. Are very easy formulas involving the previous bias and weight matrices, and also the parameters appearing in the refinability property, such as tau or A0, A1, A-1. Okay, in case that you define the neural operators in this way, you get the result you were seeking for, that is, the compositions are equal. Let's see briefly the proof how this is possible. Well, it is very similar as in the example we gave with the adding of zeros. Let's start by writing the layer operator L0. To make this simple, suppose that the neuron you want to split into several ones is the first one, so it's L0, 0. The definition of this is the one you see here, is sigma 0 applied to the first row of W0 multiplied by X plus B00, the bias. Now use that sigma 0 is refinable so that you get this sum of several sigma zeros. Observe that now we have 2 multiplied by the weights, and this is suggesting which are the new weights that you have to take. And also observing the second part, 2b minus L plus tau, this is proposing which is the new bias you have to consider. Okay, if you define in that way the layer operator L0 bar, what you are exactly obtaining is a linear combination LAL times the new layer operator. Okay, but what we want is that the composition is the same, so let's write L1, by definition is this one. Again, it's interesting to write the expression as the sum of the columns of W multiplied by each neuron, so that we can see the contribution of each neuron. Now let's make the composition of both the operators, that is the quantity we want to preserve. I highlight this part in yellow. You can forget about it because it is speaking about the neurons that you don't want to split. Let's consider the right part, that is the neuron that you want to refine. Observe that we already proved that the L00 can be expressed as a linear combination of this AL and the new layer operator L0. Now it appears the weights of W1, and again this is suggesting the new weights for the operator L1 bar. So if you define L1 bar so that these are the weights and this is the bias, that is exactly the same bias, you have obtained that the composition of the all layer operators coincide with the composition of the new layer operators. As I told you before, all these results of the slides come from this paper. There you can find also how to insert new layers, not only to make the layers wider, so you also can find how to make the network deeper with more layers. It is not based on the refinability property, but it is based on the summing the identity. That is a property that is also inspired on the subdivision theory. In that paper, you also can find how to define new activation functions with this capability using any basic limit function of subdivision schemes. That is, in the paper we particularly propose the spline activation functions, but if you desire, you can define infinitely many activation functions fulfilling this property. We have proved that these activation functions fulfill some properties that are desired in practice, like they are smooth, they are monotone, and they are bounded. In particular, for the spline activation function of degree D, we prove that they are CD-1 smooth. We give a closed formula to compute it, and also a closed formula to compute its derivative, and even for the particular case D equal to 1, 2, that are the one in the examples of these slides, we give an expression of the derivative in a backpropagation style. To conclude, we have presented a new class of activation functions to enable neuron creation and layer insertion. The neuron creation is via subdivision, while the layer insertion is done via summing the identity. In all cases, we have explicit and efficient parameter computation, and they have, and we expect this, good approximation properties since they are based on approximation theory. What's next? Well, we perform some preliminary numerical implementation, which is not included in the paper, and it shows good performance in very simple examples. Now we hope to find some collaboration with some experts in neural networks in order to test this new activation function and this new neural network growing method in some realistic problem. If you think that you can contribute in some way, or you are willing to know some details about this, you can contact me by the comments on the video or by my institutional email address. Thank you very much for your attention. I hope you find this video interesting.